Hello, everybody. Glad to be back at FiRe again this year. I have with me today Justin Rattner, who's the CTO of Intel, and Larry Smarr, who's the director of Cal IT2. The topic that we're talking about today is high-performance computing and what's next in that area. This is an area that I've been interested in for about 25 years now and have spent most of my career working in that area and trying to push applications forward to get some kind of level of performance that will work for enterprises all around the world. What we have been talking about in preparation for this panel is that when I talk to a number of people about supercomputing, and when we were talking about it, or high-performance computing, when we were talking about it at the dinner last night, one of my colleagues at the table said, "Oh, you mean SGI and Cray and IBM," and I do believe that's the perception that most people have around this field in this area of computing, but that's not the case anymore. I mean, we really are in an era where high-performance computing is not your father's IBM Blue Gene machine anymore, and that's what we want to talk about today. So to begin with, what I'd really like to hear is just your view of the context of high-performance computing, Justin, and what you see going on today.
Well, I think we're at kind of a threshold of a whole new vision and opportunity for high-performance computing. I spent a decade in high-performance computing in the traditional sense, building the biggest, fastest machines on the planet. When the government decided that high-performance computing was no longer strategic, peace broke out, as as a lot of people like to say. It became very unattractive financially. In fact, the companies you mentioned, I guess with the exception of IBM, went through a number of mutations, let's say, in order to stay in the business. But as a result of Moore's law and I think progress on the technology side, I think we really stand on a threshold of taking that technology sort of out of the national labs and literally into everybody's desks and homes and so forth. So this is, I think, for high-performance computing people, this is really a very exciting time.
I agree. It is a very exciting time. We're starting to see the transition away from, I think it was just 10 years ago, wasn't it, Larry, that we had our first teraflop machine, and that was 9,000 processors. So it was in a completely different environment today. What do you see going on today in the high-performance realm?
Well, two things I'll just mention, since I used to be the guy who bought the machines that Justin and the others created. With multi-core, what you're seeing now is that the detailed kind of parallel algorithms that Justin and others developed, the compilers for them, everything, you have to have it on your desktop, because with multi-core, and quad-core sounds fine, that's 4, but then it's 8 and 16 and so on, and you've got basically what used to be called a parallel supercomputer to do word processing. I mean, Intel actually just opened a center, I think, at my old University of Illinois in parallel computing, because they need to get those ideas that we pioneered in supercomputing down to everybody who owns a personal computer. But the other thing is, you'll notice I'm not a supercomputer center director anymore. I gave that up when I left NCSA in 2000, and the reason was that even at the high end of performance, I was seeing that the national and global systems were becoming greatly unbalanced, and that the soda straws of the internet, the shared internet, that you're trying to get to the gigabytes, terabytes of data that these supercomputers can generate, there is no way you can haul it across the net. I mean, if you're getting, say, 10 megabits a second over the shared internet, a terabyte is going to take you nearly a week to move it at that speed. It's just crazy. So I decided to look at the technologies of super networks with optical fibers, super visualization, the sort of things you're going to see tonight at Cal IT2, and that then those weren't just for supercomputers as data generators, but in fact for data being generated everywhere around the Earth, or as Curtis Wong will show you tonight at Cal IT2 with his worldwide telescope, from the great observatories in orbit. So there are vast numbers of scientific instruments generating data. There are federated repositories of data all over the planet. And what you want is for those bits, once created, to flow freely. And they aren't today because of the shared internet architecture. It is possible to use the same fiber to give you personal light paths at 10 gigabits a second, and we'll do that tonight worldwide. But this hasn't really taken off commercially yet. It's not even in the National Science Foundation's cyber infrastructure plan, in spite of the fact the United States has a national lambda rail which allows for multiple 10 gigabit dedicated pipes to all the major universities, or even a global lambda integrated facility, which is the same thing but on a global scale. I don't understand why we aren't looking at this system as what it is, which is a global information system, and therefore we should, as engineers, be architecting it so that there's no bottleneck. Instead, we put bigger and bigger critical paths, like making a bigger supercomputer without making bigger super networks. So that's where I've been focusing on.
Right, and I think you're absolutely right, Larry. We have been looking at nodes on the networks, and they're isolated, and the paths between them are arcane and small, and don't work and don't give us the bandwidth we need to move between those machines to actually have a computing environment that is global in nature. Do you see any way to get past this, to build out that network in short order? Are people aware of this as an issue, or is this just something that a small cadre of people are aware of and it hasn't risen up to the consciousness level yet?
Well, the beauty of the fiber optics is because the infrared lasers are in the micron range, you can actually have multiple channels going down the same fiber, even though it's like the thinness of your hair. Your long-distance telephone calls are going over the telecom carriers, and they have like up to 40, 10 gigabits or even 40 gigabits per lane. And so I think it's really the development of the telecom carriers of new services to allow you to continue to use the shared internet for what it was designed for, which 30 years ago, which was email and small FTP. So the average web object you move is about a megabyte. Your PC and the internet have been co-engineered and co-evolved so that that goes interactively. It's sprightly, right? But a gigabyte is 1,000 times that.
Yeah.
And for scientists, that's what we want. We want to have the same sprightly performance that with objects 1,000 times larger than you do, and so you have to make everything in the system 1,000 times larger. Now, but the way the market works, that will be what you have at home 10 years from now.
That'll be nice. Now, one thing that you'd mentioned, Larry, and I want to turn to Justin on this, is that Intel has opened parallelization centers in Berkeley and at U of I, and you and I have talked briefly about some of the challenges in parallel programming. Where do we stand? What are those parallelization centers tasked with doing, and where do we stand on overcoming this problem of parallel programming?
Well, we got the idea, actually talking with some of the folks at Microsoft. We got the idea of creating these centers because I think we recognized, and did many others, that the state of parallel programming wasn't what it needed to be to really enable the mass of software developers out there to really to apply the technology. In fact, we made the observation that few, if any, PhDs were coming out of graduate school having ever written a parallel program. It didn't even seem to be a requirement for a PhD, and the teaching of parallel programming, was almost almost unknown. And we had taken some steps a few years ago. We started to create curriculum material and work with universities, not just in the U.S. but around the world, to begin teaching that. But most of that technology is actually the technology that was created, a decade or two ago. And in fact, when I started, looking at this again, having been away from HPC for about a decade, I was shocked by how little progress there had been. I think I've annoyed a number of my colleagues by describing the lack of progress, so bluntly. But not much has happened. And I think we PPL, and I'm sure others are going to emerge
as well.
In the near future. So and the community is excited. In fact, when we were looking at the proposals we got back from the call and talking during the site visit, it was really exciting to hear the department saying, this is the first computing problem in a long time that's really brought the department together. Exactly. We've sort of all gone off in our different little areas, but this may be, in fact, John Hennessy said to me a few months ago, this is the grand challenge for computer science, and now's the time to get it solved and to bring together the academics and the industrial researchers and really solve it once and for all.
Mm-hmm. Well, I'm firmly ensconced in the enterprise market, and the software that we're working on is enabling companies to build databases that are factors larger than anything we've been able to build in the past. I mean, we just did some benchmarking on quad-core processors showing that we could analyze 330 million rows of data per second per processor. So we're getting to a point now where we can actually get some real throughput through databases, through networks, through processors, through disks, things like that. One of the things that we were talking about in preparation for this panel was the absolute explosion of data. Now, when you talk to the people in the enterprise market in the United Kingdom, in the United States, Latin America, Asia, I get the sense that they believe that we're at the peak of that data generation slope. And I'm just stunned to hear people say that because I know it's not true. So I'd like to hear both of your perspective on where we are on the explosion of data.
Oh, we're just beginning to start. I mean, you see, for a long time, it was the supercomputers that generated the data. And so that wasn't a problem because there were so few of them. But now if you go to like a college campus, the number of professors that have genome sequencers, DNA arrays, microscopes, every one of these things has got these processors in it. So those things are like shooting it out at a gigabit per second, right? And then the guys figure out, oh, I had enough money to buy the instruments, but now what am I supposed to do with this billion bits a second? Oh my God, there's another billion bits, and now another billion. Where am I going to put all these? They don't know how to build a data center or anything else. And so I think there's a kind of a new data utility where you just plug into the fiber in the wall, and then you build very large data caches on campus. You're seeing what Google and Microsoft and all the others are doing with these mega complexes that are just cached at different levels. And so the data exponential, it's not just that each instrument is going to be on Moore's law, but the number of them that are beginning to be sources of data are just unbelievably vast. So you're going to see a super exponential over the next few years and the number of bits that have to be stored, analyzed, and visualized. And that's why we're driving this business. I mean, tonight you'll see a wall with 220 million pixels compared to the one that you're looking at there or on your desktop. Why? Because how else are you going to have enough visual real estate for the human eye-brain system to do its pattern recognition thing with the quantities of data and the complexity, like biological complexity, climate complexity? These are things that you've got to see the global aspect at the same time you see the details. And so you haven't seen anything yet.
Well, and I think that, the growth in bits, I think, just from an individual point of view, is is really staggering. I had some CAT scans a few years ago, and I thought it was very interesting. They handed me a CD instead of a film. And I said, "Can I get the film?" And they go, "Not unless you pay extra." So the bits were coming that way, but you're gonna carry around your gene sequence, which is going to take some space. I mean, the instrumentation is cranking out immense amount of information. We were actually more motivated, I think, in our work in what we call terascale computing, which is sort of bringing those terascale machines of a decade ago down to the desktop, really more by the problem set. And it's interesting, Larry basically covered two of the three domains that we focused on. We focused on recognition, right, which is how do we find what's interesting in the in the data? How do we spot the important things? How do we process the vast amounts of information? How do we mine it? So that's the second piece, so R and M. And then how do we synthesize, you know, the future based on our ability to recognize and mine the data? And in each of those broad categories, you know, we discovered an unlimited amount of data and therefore an unlimited amount of computing that had to be applied to, you know, get the knowledge out of all that information.
Mm-hmm. And another thing that I talk to people about, and I get that look back at me like I have 3 eyes or horns growing out of my head, which maybe it's just me talking, but or whatever. But when I talk to enterprise customers about taking analysts out of the loop and instead inserting machines in the front of the loop. So, you know, the synthesis of the data is immense and growing rapidly, and you know, there's just no stop to it. And it's getting to the point now where humans have a hard time understanding the entire problem space. So can you talk a little bit about, you know, inserting the machines into the front of the process and doing the initial pass on the filtering of the intelligence and the data?
Absolutely. I mean, you're going to have intelligent software agents that are the primary first responders to get in there and sort out from this vast data flow what are the interesting anomalies, the things that you want to bring to the attention of a human. And these are just beginning to be developed. I mean, to give you an example, last year we were at Cal IT2, you saw a single high definition flow from the ocean bottom. Well, you know, there's now an ocean observing initiative, and there'll be soon tens, hundreds, thousands of these high definition cameras underwater 24/7, 1.5 gigabits a second as HD. Who's going to find all of the critters and the interesting events and so forth? Not that many humans. So we're actually doing computer vision work now to spot, classify, and so forth, come up with census of these things in environmental systems. Because we have to learn how to monitor the environment. You know, Mark's been talking about how we're going to have to deal with global change. It's a big globe, and you don't know how it's changing locally unless you have already had sensors that are giving you the current state of the environment in this patch on the planet. Same thing, the 3/4 of its ocean. We know nothing. We know more about the surface of Mars, which you'll also get to see tonight, than we do the surface of the Earth, because it's 3/4 of it's underwater. And so, although there is something known, it's not the level of accuracy. And so how are we going to get the software systems? And I think this is where we lose a lot of times. We talk about the hardware, but the software is much more difficult to develop. And it's also the motivation to do it. I mean, I know that all this stuff seems so esoteric, like supercomputing. You're like, okay, yawn, who needs that? But remember, you know, I mean, you have these gigahertz quad-core PCs you're all on. Well,
3 gigahertz.
The first
3
one,
gig, yeah, right.
first 1 gigahertz I had was a Cray 2, 4 processors in 1988. It cost $15 million. Same, actually, less speed, less memory, right, and less disk drive than what you got on your PC. So the supercomputer really does tell you about the future, because that will end up in everybody's hands.
So I'll give you the non-esoteric consumer application, which drives the software. And in fact, you know, I've really, you know, worked hard with my colleagues at Intel to try to create this vision, you know, beyond the big science. Our team in Beijing developed a parallel application that watches television. And you say, why do I need computers to watch television? Well, quite frankly, I don't have enough time to watch television. Most of the people in this room don't have, you know, time to watch television. And, you know, TiVo goes only so far, right? I mean, every time I bring up that list of things I've recorded on my TiVo, I just got to run for cover. I'm like, oh God, I'll never get back to this. So, but they had this idea that if you could have the computer watch TV, then the computer could create the highlight reel for you, right? It's sort of like Sports Center on demand, right? Now, of course, all those programs, the billions of bits in those programs in high def, are being stored away someplace online. So what if you had a program that could actually watch those when you can't? And in the case of sporting events, build a highlight reel, but not build it, of course, the way they do on ESPN, where some guy's sitting there, saying, oh, that's this player or that player, or there's the shot, or there's the hit, or there's the touchdown, whatever. What if you could say, hey, these are the players I'm interested in. These are the game highlights I'm interested in. Maybe I want to isolate on a player. Maybe I only want shots on goal, et cetera, et cetera. And the computer just looks at it, identifies all of that, and creates that reel. And then when you have very little time, maybe 5 minutes, you get the custom reel. The computing demands are every bit as intense as what Larry's described for looking at the oceanographic information. But it's a very personal service, right? And so I get a product delivered to me, electronically. That's just what I have time to see. When I think about my kids, and all the IM windows and all the other, Facebook and MySpace, all the stuff going on, right? That's how they're going to watch television in the future. They're going to watch all these little highlight
snippets.
Reels.
Right, snippets. Yeah, that's a great idea. That's actually TiVo I could use. I use TiVo now, but that would be even better. We're at about 6.5 minutes away from wrapping this up, so we're going to open it up for questions in about 1.5 minutes. So try to think about what you want to ask. I think it was 2 or 3 weeks ago, Mark was exhorting all of the FiRe members to, start thinking about optical computing and how that's going to work. And has that entered into the realm of consideration in your world, Justin?
Yes.
Well, I guess it was quantum computing.
Well, quantum computing is a little bit different. They may share some things, and I won't try to pass myself off as an expert in quantum. But we do a lot of work in photonics, and to Larry's point, there's I think there's a lot of opportunity to move more of what we've traditionally done with electrons to photons. But the very reason you can push all of those colors down that single fiber is the very reason why optical computing has turned out to be so limited. And that is, photons don't want to interact. And to actually carry out a computational process, it helps, at least at certain points, to actually have photons interfere with one another. But that's proved very difficult. So there's a class of computations that, that are useful and important that can be done optically, but it's a fairly limited class. And I suspect that quantum has similar characteristics, that maybe it's more versatile, more robust, but I've yet to see someone walk into my office and say, hey, I've got a quantum computer that can replace all of this charge-based electronics that we've been working with for decades.
Yeah, I made it work. Get rid of all that stuff.
Yeah.
Yeah, exactly. Larry?
Well, I'll just say we have an opportunity on Friday to meet with D-Wave Systems and talk about quantum computing.
Very good. All right, we're wrapping this up. So, any questions out there from the audience? Anybody want to pose Mr. Peoples? Good. Good to see you.
Microphone on the way.
Oh, there you go.
Oh, there.
I was wondering.
Just keep talking.
I was wondering, 2 years ago we had China Mobile here. And the thing that really confused me was how they did information with 600 million subscribers, wanting to know where Bob is all the time. And they were number 6th in the China telephone business. So there's somebody that has billions, I guess. So how would you do information management on a phone system when everybody wants to know where Bob is?
You could talk about the number of
exactly.
rows you can do.
I mean, we're building database systems right now that can certainly handle that volume of transactions very easily. I mean, we're set up to we can parallelize load streams to n degrees, where we can load them into databases and we can rip through those databases like a knife through a hot knife through butter. So that's really not an issue of managing the flow of transactions into a database and doing the analysis on it. That's very easy at this point. We would actually set up a cluster of different systems to ingest that, analyze it, and shoot it out. The real question, I guess, that I have in my mind is how you would do it from a transactional perspective versus an analytical perspective. But then again, that's just a hardware engineering problem. But we're getting to that scale now where I'm having a conversation with a company right now about a 500 terabyte data warehouse that gets 100 terabytes of updated data every day.
Banks do that. I mean, it's not a big, you know, we didn't mention that the US government, as well as others, are funding now petascale machines. So instead of 1 billion you were talking about, your laptops are doing 1 billion floating point operations per second. A petaflop is 1 million times faster than that. And in 2011, University of Illinois at Urbana-Champaign, NCSA, my old center, will take delivery of the first 10 petaflop peak sustained petaflop machine, generating 1,000 teraflops or 1 million gigaflops per second. So that's where the point of the Spear is. On the other hand, you know, as I say, you now have a Cray 2 much faster than a Cray 2 on each of your PCs. So, you know, if you look out 10 or 15 years, having these kind of capacities in all your homes, having wallpaper, you go down to Home Depot and get this electroactive, it's got 1 billion pixels per wall, I think is very likely routine.
Anybody else? Okay.
I'm not sure if this is exactly y'all's area, but you talked about the computer that watched TV for you and TiVo. I was wondering if y'all would speculate if it's cutting out so much and making the highlight reels, what are advertisers going to do?
Adapt or die.
Right. Do you think they'll overlay their images onto those highlights, or?
Yeah, well, there are whole businesses right now set up, and whole business models set up on product placement. You know, making sure that you know, whoever your favorite star is in whatever reality show is drinking a Coke versus a Pepsi. And
well, there's that. I guess, yeah, we could certainly do that. But no, actually, I think it dramatically expands the opportunities for advertisers, because now you're delivering a very personal product, information product, and you know, rather than, well, I'm just buying this one, you know, this one spot on this one show, you know, that, by the way, most people are going to TiVo past anyway. Yeah. Right now, I mean, I can get those insertions right in that, you know, in that custom product, and you know, I can make the trade-off. Do I want, you know, if I want to pay for it, I can get it without those spots. If, you know, if I don't, I get it with those spots. So actually, I think these information products create extraordinary amounts of advertising opportunities that are targeted. I mean, you've got somebody telling you, this is the information I want to see. So you got their eyeballs, right? And I don't have any concern that that's going to somehow reduce the advertising potential. I think it's going to increase it dramatically, and highly focused at the same time.
we are capitalists. We will figure out a way to make money. Thank you very much.